Chapter 31, Theory Video 2. We are going to discuss luminosity and radiant flux intensity. So we know the Sun is the nearest star to the Earth. Then the second nearest star is Proxima Centauri. That is 4 into 10 to the power 16 minutes away. Meters away. 4 into 10 to the power 16 meters away. So this such a big distance is actually not something easy for us to get an understanding of. So as a result, we use light year. So you know the definition of a light year. So that is the distance of light travels in a vacuum in a time of 1 year, that is 365 days. So 1 light year is equal to is quite similar to there is a you can get a numerical value to that by multiplying 3 into 10 to the power 8, that is the time, that is the length light travels in a second, that multiplied by 365 multiplied by 24 into 3600. So that will give you 9.5 into 10 to the power 15 meters. So then when you do the calculation, you will understand that Proxima Centauri is 4.2 light years away. So that is, if you travel at the speed of light, you will take 4.2 years to go there. Then at the same time, the light of Proxima Centauri will come to the Earth in 4.2 years. So you know it is actually easy for us to understand how far they are. So Sun is quite close by. It takes 8 minutes for us to reach the light to reach the Earth from Sun. So the distance in light years is 1.58 into 10 to the power minus 5. So that is that is something that you need to understand. So the temperature on the Sun is 5800 Kelvin. Luminosity is taken to be 1. Then Sirius, it is 8.6, 9925, like that. There are different luminosities and different temperatures on them. So as you can see here, in Canopus, which is 310 light years away, it has a luminosity of 1100. So as a result, we can figure out that a star's brightness will depend on not only its distance but also its luminosity. For example, if you take Canopus, it will be really bright. It should be really bright, but however, because it is 310 light years away, there would be a reduction of that that brightness in relation to other closer stars. Now Alpha Centauri is brighter in the night sky than Arcturus. Arcturus is 37 light years away. You can see that it is 170. Luminosity is 170. Now when you take Alpha Centauri, it has a luminosity of 1.5. But because it is really close, 4.4 light years away, Alpha Centauri is brighter than Arcturus. It is not because of the luminosity, because it is close. Then later on we will figure out that the luminosity of a star will depend will not only depend on its surface temperature. So when you consider its temperature, higher the temperature, you can actually reach to a common or a basic understanding that the higher the temperature, higher would be the luminosity. However, the physical size will also have an effect on how luminous a star is going to be. Um, so if we relate the brightness of a star to its luminosity, we have to make some assumptions. That is, if the power from the star is uniformly radiated through space, then between the star and the earth there is negligible absorption of the radiated power. So then, based on these assumptions, we can actually determine the intensity of the electromagnetic radiation, and then using that we can reach different conclusions. The observed intensity of this electromagnetic radiation is known as radiant flux intensity F, and this is defined as the radiant power passing normally, that is at 90 degree angle, through a surface per unit area. So to calculate this F, that is the radiant flux intensity, to be calculated from a distance d from its center, from the star's center, we use power of star divided by surface area of the sphere. The power of the star is its luminosity L, and the sphere's surface area is 4 pi d squared. So F equals L upon 4 pi d squared. L is the luminosity. Then SI units for radiant flux intensity therefore is going to be, because L is the power, it is watts per meter squared. For any given star, for a particular star, luminosity is constant. So as a result, the radiant flux intensity will obey an inverse square law with distance. So if you double the distance from the center of the star, the F will decrease by a factor of 4. So if you triple the distance, it will decrease F by a factor of 9, etc. So this inverse square law can be inverse square law can be demonstrated using a filament lamp and a light meter in a dark laboratory. So it is, we consider the bulb to be a star of luminosity L, and we change the position of the light meter away from the object and see how it happens, how it is reduced. Write down a note. Distance between galaxies and stars is calculated using light years, simple L, simple Y, because if measured in meters, the distance would make less sense. Leave a line and write. Light year is the distance traveled by light in a vacuum in a time of 1 year. Therefore, 1 light year equals speed of light in vacuum multiplied by 1 year in seconds. That is 1 Ly into 3 into 10 to the power 8, that is the speed of light in 1 second, multiplied by 300. To convert 1 year into seconds, you multiply 365 days into 24, then it is hours. Then 60 into 60 is 3600, because an hour has 60 minutes and each minute has 60 seconds. So 60 into 60 is 3600. So 1 Ly is more or less similar to 9.5 into 10 to the power 15 meters. Leave a line and write. The brightness of a star will depend on the distance from the Earth and its luminosity. When we relate the brightness of a star to its luminosity, we make following assumptions. Number one, power from the star is uniformly radiated through space. Number two, there is negligible absorption of this radiated power between the star and the Earth. By using the intensity of electromagnetic radiation based on these assumptions, we can calculate the observed intensity, put a dash and write radiant flux intensity, capital F. Leave a line and write radiant flux intensity is defined as the radiant power passing normally through a surface per unit area. So the equation is radiant flux intensity equals power of star divided by surface area of sphere. So F equals L upon 4 pi d squared. Therefore, SI unit of F or radiant flux intensity would be W watts per meter squared. As a result, for a given star, luminosity L is constant. Radiant flux intensity F obeys an inverse square law of to D, within brackets D is the star at a distance d from its center as a result. Doubling the distance from the center of the star will decrease F by a factor of 4. Tripling will decrease F by a factor of 9, etc. Leave a line and write. This can be practically demonstrated. This inverse square law can be practically demonstrated using a bright filament lamp and a light meter in a darkened room, darkened laboratory. Now, so using this radiant flux intensity that reaches the Earth, we can use F equals L upon 4 pi d squared, and then we can determine the distance d by rearranging the equation if the luminosity L is known. So if there is a standard candle, that is a celestial object whose luminosity is known. So if you have a Cepheid variable star in a distant galaxy, we can figure out, using the period, we can figure out the luminosity, and by finding out the luminosity, we can find out the distance that it is from. So in this worked example 2, the distance of a star in the Andromeda galaxy is calculated from the radiant flux intensity at the Earth. So here what has happened is the radius of the Sun is 6.96 into 10 to the power 8 meters, and its luminosity is 3.83 into 10 to the power 26 watt. The orbital radius of the Earth is 1.5 into 10 to the power 11 meters, calculate the radius flux intensity at the surface of the sun and at the position of this of the earth. So what we do is we calculate the radiant flux intensity at the sun's surface using F equals L upon 4 pi d squared. We substitute the values, luminosity has been given. We know that it is 6.29 into 10 to the power 7 watts per meter squared. Then we calculate the radiance flux intensity at the Earth's position by using the inverse square law relationship between F and D. We can find this. The distance would increase by a factor of 1.50 into 10 to the power 11. That is the orbital radius divided by the radius of the sun, 6.96 into 10 to the power 8. That will give you 215.52. So as a result, what it means is F will increase by a factor of 215.52 to the power 2. So as a result, you will get F is equal to 6.29 into 10 to the power 7 divided by 215.52 squared, which is going to be 1.35 into 10 to the power 3 watts per meter squared. So if that is the using the inverse square law. If you use F equals 1 upon 4 pi d squared with L being 3.83 into 10 to the power 26 and watts and D being 1.5 into 10 to the power 11 meters, we will get the same answer. We will get the same answer, that is orbital radius of the Earth, taking that as the same value. I hope you understand. If you did not understand, try to do the questions. If you cannot do it, you try to do substitute these values and see in both ways, then you will understand it. If you don't understand it, let me know, then I will explain it further. And if you don't understand the calculation in relation to the inverse square law, again raise questions, then I will explain. Now the second example is the radiant flux intensity measured at the Earth from a Cepheid variable star in Andromeda is 1.4 into 10 to the power negative 16 watts per meter squared. The luminosity of the star is 1 into 10 to the power 30 watts. Calculate the distance of the star. So we have to first calculate the we have to first make D the subject. So we get square root L upon 4 pi F. So we simply substitute the values that they have given. The distance would be 2.4 into 10 to the power 22 meters. If you divide it by light years, light year meters, then you will get 2.5 million light years. Write down a note. By rearranging F equals L upon 4 pi d squared to obtain D and knowing the luminosity and the radiant flux intensity, we will be able to calculate the distance of a star. Now, inverse square law for radiant flux intensity is the practical activity that is important. So now what we do, the scenario is we have a bright filament bulb and a light meter. So in the commercially available light meters, they don't show radiant flux intensity in watts per meter squared, but they measure everything in a quantity known as illuminance. My apologies, illuminance. So if we say the illuminance is in a unit called lux, is directly proportional to radiant flux intensity. So if you carry out the experiment, that is, you double the distance, and then you will see that the illuminance is going to be reduced by a factor of 4. Because radiant flux intensity is inversely proportional to d squared and directly proportional to illuminance. So if you draw a graph of illuminance against 1 upon d squared, it will be a straight line through the origin. Please try to understand what this means, and also you should be able to explain what this means by using the graphical simulation. So please try to read through this and listen to the details, and if you have any questions, please ask. Now do the questions from 1 to 5 before moving on to the next video.